Hello and welcome to this 5-minute short on using Piper to do your inlet pressure loss, your back pressure around relief devices. So this is a three-parter. When we start getting into using Piper, we're looking at non-ideal gases, or we're into supercritical flow, into two-phase flow. So it's a little bit trickier. Piper has less fittings, so we need to be a little bit more imaginative how we do this and how we build this up. So we're going to do this over 3 parts. The first part is we're going to build our relief valve model. Part 2 will then be looking at building the back pressure, and then part 3 will be looking at the inlet pressure and how we bring it all together at the end. So first of all, let's build our model. So again, in true Blue Peter style, which is definitely one for the kids, I think. Here is our model and pre-built to here. So we've got a contraction and then an enlargement. That's how we're going to model this particular device. A little bit of pipe in the middle, if I just double click on that pipe. So it can be 0 length, that's fine. So it's not going to appear in the results. It's just connecting the two pieces together. This in effect is representing our orifice. We've put a diameter in here, so I've put 22 millimeters. But where did that come from? So if I go back to my initial calculation sheet, what I've done is, this is from an earlier 5-minute short, a relief device sizing, direct integral method, and down here I've got a KDA, 325, so that one, 316 square millimeters. So I've used the function, the diameter function, to convert that square millimeters into a diameter, which is about 20 millimeters. Now, that's not 22, I know, it's 20 and a little bit. What we'll find is when you're using this is obviously the API is making some assumptions. So that particular sheet is assuming you've got some sort of, you're doing an isentropic flash through that valve. If you use normal APIs, 520 equations, it's assuming an ideal gas. We're making some assumptions around the orifice and KDs. And of course, Piper's got its own correlations and that kind of stuff. So we're not going to get these things exactly right. We're just trying to mimic that relief valve. Now, obviously, if I ran this and that was like 3 foot, then that's going to feel a bit funny. Something's wrong. So certainly want it to be close. How close isn't going to be an answer. It's kind of, again, it's this engineering judgment. Does it feel about right? Am I comfortable? But fundamentally, what we're trying to do is to create a model here of the relief valve and exactly what's happening there. I'm not trying to design the insides of it. I just want to make sure I get the flow rates through it correct, so I can understand what's happening on the inlet side and on the back side of it. So that's where we're trying to go with this. Physical properties. We're going to pass some material through this. So again, you'll have seen this on other ones, but we just put toluene in. So we just search for toluene, selected toluene, just we've done on many of these before. Then we're going to go to the conditions. Now the conditions is a bit fun. So a little bit different to the way we do this with Adrian. So this time we're going to specify an inlet and exit pressure. So we're going to specify our relieving pressure. So again, I'll just show this 6.6 bar gauge. And then back pressure, we're going to go to atmosphere, so 1 atmosphere. And this is putting it in pascals absolute at this point. On this side, because Piper can handle two-phase flow, we need to be a little bit smarter how we specify the conditions. So I've got a fire case, so I'm going to specify it as a mass fraction of 1, so it's going to be at its bubble point. If I wanted the temperature, I wanted it above the bubble point, or wanted it all liquid, I could specify a temperature there. Obviously, if it's two-phase, I can't specify that temperature. I'd have to specify a mass fraction, so because there's obviously the temperature consistent. So just need to think a little bit about what we're doing in there, of how we're specifying this stream. We need to provide some estimates. So Piper is iterative, so we need to provide some estimates around that. And again, where I've come to that is go back to my sheet. So I'm going to do this on the rated capacity, just to keep this a little bit easier at this point. And I've assumed KC is 1 again, just for the purposes of getting through a Piper example without complicating things too much. Now, when you first use this sheet, this will say kilograms an hour down here, but we want to see it in kilograms a second, so I can just type kilograms a second, and it'll tell me it's 0.75 kilograms a second. So again, that's how we will handle and can play about with units in Capri. So I've got my range, so I've gone for 0.1 to 1. I need 0.75-ish. And then I press OK on that. And that's basically it. Now, as you'll see in the next couple of these, this model's going to get a little bit, I won't say complicated, but your eyes are going to sort of start crossover. I'm going to say, what on earth is the valve? What's not? So what I'm going to do is just make that valve look a little bit more obvious when I start making the model a bit more interesting. So I'm going to draw a rectangle over it. So you can draw these things over this. And then, of course, we'll need to send that to the, let's send it to the back. So we've now got a little box that's representing my relief valve. And I'm even going to mark it relief valve. You'll see why this is useful later on when your eyes start to cross over. But that's my little box. That's my relief valve model. And I'm all good to go. So I'm going to press calculate. Pipette is going to twirl away. And then we've got some results down here. So let me just bring this up a little bit. So what I'm seeing here is, again, I can hover over these. You can see the red light on the Piper model, so we're showing what's happening. We can see we've got our pressure discontinuity, so we're choking. So that's good. So we're choking inside that valve. We've only got a static pressure in Piper. We haven't got stagnation pressure, so we'll need to come back to that and think about that when we're doing our inlet pressure drops. But you can see here, now it picks up that this final point here is at 0 is atmospheric pressure. Key bit 0.75, so that's good. So I've got 0.75, give or take 0.7. So that's going to be close enough for what I'm trying to do. Very hard to get it exact. And that's fundamentally what I need to do, getting set up as a model. I then need to think about what next and start building up the pipework. And that'll be part 2. Thank you very much.